Hello everyone, welcome to my channel. My name is Tiago, and in this series of videos we are solving algorithm challenges that we find on the internet. The ones that we're solving recently is from Project Euler.net. And in the previous video we solved the Project Euler's problem number 10, which is this problem here, named the summation of primes, which asks us to find the sum of the primes below 2 million. We successfully solved that problem with the functions that we had implemented before to generate prime numbers. However, the solution that we achieved was slightly slow. It took a few seconds to compute, and I think that we can make a faster implementation to solve this problem using new ways to generate prime numbers. And in this video, we're going to try one of these new methods to generate prime numbers. So let's go to it. The one that I like the most is one called Sieve of Eratosthenes. The Sieve of Eratosthenes actually is an algorithm to identify prime numbers within a given limit, right? It works like this. Actually, you start with list of all numbers as prime, and you start from the bottom of this list. And if you find a prime number, you automatically know that all the multiples of that number are not a prime. So for example, 2 is a prime. We know that 4, 6, 8, 10 is not a prime. So we can automatically discard them all the way to your limit, right? Same thing for the next prime number, number 3, right? We already know that starting from the square of that number, 9, all of the multiples are not a prime number. So 9, 12, 15, 18, they are not prime numbers because they are multiple of 3. And then we can go through this list until we find all the prime numbers. The ones that are remaining are the ones that are primes, right? So we can just ignore all of those, right? This is actually a clever way that we can make a list of prime numbers that are quite fast to implement this. Actually, I like this algorithm very much because of its history, right? The name, the Sieve of Eratosthenes, it's not here by chance, right? Eratosthenes was a very clever guy that lived 2,300 years ago. I think it's in the 3rd century BC, right? So he was a Greek mathematician and one of the most intelligent persons that ever walked on this planet, right? I believe that he came up with a very interesting algorithm even before computers were a thing. So this is actually quite clever, a clever way. And the complexity of this code is the O of n log of log n operations, which is way faster than what we have right now, which is just the O of n multiplied by the square root of n. Right? Every time that we find a complexity that has log on it, it's usually faster. There are faster implementations of the same sieve, right? Some that use bit complexities and others that use different implementations that can go even further. But we're going to implement the root implementation of a Sieve of Eratosthenes. I think we can implement this and see how it compares to our current implementation, and then we can make this comparison, right? So let's try it. I'm going to implement it in our prime functions here because this module is all about prime functions, right? I'm going to call here Sieve of Eratosthenes. I hope yes, I wrote the name correctly. I hope so. Nope, I did not. Eratosthenes, yeah. And it requires a limit. So I'm going to give this limit, and it returns a list of numbers, which is going to be our prime numbers, right? I want to implement in this way. So our Sieve of Eratosthenes, it performs the Sieve of Eratosthenes to find a list of prime numbers within a given limit. And this should be upper boundary to check, and the return should be the list of primes, right? So how this is going to go? Sieve is a good name, right? And all the elements initially in this sieve is true, so we can either do something like this, I in range limit, so we have a vector of just the true, limit, it contains all the numbers from 0 all the way to the limit, in our case 2 million. And we know that like 0 and 1 are not prime, so we need to add them here, right? So the sieve in the position 0 is not a prime, and the sieve in the position number 1 is not a prime either. So it means that like we're just setting it to false, indicating that it's not a prime. So now the idea should be that we go through all of the primes that there is, all the way to the square root again of the limit, and we perform the sieve. For that we have to loop. I'm gonna call it prime in a range starting from 2, right? This is our initial prime, all the way to the math dot the square root of limit plus 1. Right, and we know that we have to transform that into the floor function, so we go that. Yeah, we can do like this, right? And then when we check the position, we have to check if it's already a prime, so we just check if the sieve in the prime position is true, right? Is true, or we can just write like this. And if it is, then we have to go through every multiple of that number all the way to the end and mark everything else as false. So we can go to the multiples, starting from the square of the same number, right? Or this one, all the way to the limit. And we can step at we can place ourselves in the size of the prime here that we're looking for. So for example, it's 2, we go 2 by 2. If it's 3, we go 3 by 3. If it's 5, we go 5 by 5. We don't have to check in between because it's already checked. So we can go by prime. And what we do here, we just mark them as false because they are the multiples. We don't care about them, right? So what remains is the true prime numbers, right? All of the others are not prime numbers, right? So we can just return the list. So we can just go like for a number I in range sieve, right? If sieve in the position number I is true. And we can just return the I. That ought to do it. Oops, this should be the limit, right? And this should give us a list of prime numbers up to a certain boundary, right? Let's give it a shot here to see how it works. I'm going to comment the first part of my code here, and I'm going to import the sieve. Let's test if our function is correct or not, okay? So let's print the prime numbers up to, let's say our limit should be 100, right? Let's see if this is going to work. Something is not right because it's starting from 10, it's not giving the right numbers. Let's find out what we did wrong. So we are initializing the sieve, setting 0 and 1 as false for each prime in the range of 2 all the way to here, okay? If sieve for each multiple, starting from the square of the prime all the way to the limit, we step in prime, sieve is equal to false. And then we are returning I for every I if I is true. That is interesting. I thought that this would solve. Let me just print sieve here first for us to understand what's going on, right? So we start with a lot of falses here. 0, 1, 2. 2, why 2 is false? 2 is not false. Why 2 is false? Print prime. I found out the problem. It's here. I had like prime here. This is not prime. We have to set the multiple as false. Now it should work. We don't have to print this as well. Yeah, so here we have like the prime numbers 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, all the way to 100. I'm not so sure if these are prime numbers, but I believe they are. To test that, we can just test our function now, if it's going to work in our limit, right? We know that our limit is 200. And then we have like our list of primes, not 200, 2 million, right? And then we have our list of primes. And from our list of primes, we can just sum them up, right? So our result will be the sum of the primes. This should be our result. Yes, I think this is right. Just to compare here for our result, right? Let's just see here if this is correct. The answer is 142, 92, 38, 28, 922. I think this is correct. 142, yes, this is correct. So let's find out how faster this is in comparison to the other one, right? So I also want to do a profiling here. And a profiling here. Let's compare the two solutions, right? So time for sieve, time for individual check. Let's compare the two solutions, right? So we're running both solutions here. The first solution takes 4 seconds to run, and the solution using the Sieve of Eratosthenes takes 0.15 seconds, right? So it's like in the same machine, the same conditions, it takes like 4 to 5 times faster than the initial solution. So it's way more scalable, and the complexity is way lower than this one. So while this complexity is the square root of n, this is just like n log n, right? So this is quite smaller. So yeah, it shows us that like we can solve the same problems with better algorithms, and we have a faster and more efficient code that require less processing time. Right, so I hope that you enjoyed this solution. We were able to solve this problem in 2 different ways, and our solutions here may be useful for future problems, so I'm going to keep them. Thank you so much if you liked thank you so much if you liked the implementation here of the Sieve of Eratosthenes. Let me know if you want me to make any other implementations of prime numbers, if there are any questions, so that we can solve them. And if you liked it, please like, share, subscribe, hit on the notification bell, and we talk next video. Bye bye.